In 1956, a gleaming silver train shaped like a jet aircraft pulls into Chicago's LaSalle Street station. Passengers stop and stare. The locomotive has no visible wheels from the front, just a sweeping nose cone that looks like it belongs on a runway. General Motors built this machine to save American passenger rail, and they spent a fortune telling the country it would. The Aerotrain was fast, futuristic, and marketed as the answer to everything the railroad industry was losing to highways and airlines. Within a decade, every major railroad that tested it had quietly sent it back. Not because it was slow, not because it broke down, because the fundamental physics of the design made it unfit for the job it was built to do. This is the story of how the most aggressively promoted train of the jet age failed not in the boardroom or on the test track, but on the rails themselves. The engineering looked sound on paper, the economics made sense, the reality did not. And in railroading, reality is the one thing you cannot redesign. To understand why General Motors built the Aerotrain, you have to understand what was happening to American railroads in the early 1950s. The passenger train was dying, and everyone in the industry knew it. Ridership had peaked during the Second World War when gasoline rationing forced millions onto trains. The moment the war ended, those riders bought cars. By the mid-1950s, the interstate highway system was under construction. Commercial aviation was expanding into every mid-sized city, and railroads were hemorrhaging money on passenger service. The numbers were brutal. Railroad after railroad was petitioning regulators to discontinue trains that ran half empty. The Pennsylvania Railroad, the largest in the country, was watching its passenger revenue collapse year after year. Union Pacific, Southern Pacific, Rock Island, all of them were looking for a way out. The conventional wisdom said the problem was cost. Traditional passenger cars were heavy, expensive to build, expensive to maintain, and required massive locomotives to haul. A single Pullman sleeper weighed close to 90 tons. A full consist of 12 or 14 cars demanded enormous tractive effort just to get moving. The fuel bills were staggering. The maintenance was constant. General Motors' electromotive division looked at this equation and asked a question that seemed logical at the time. What if you made the train radically lighter? What if you stripped out the heavy steel construction, replaced it with something closer to highway vehicle technology, and produced a train that one modest locomotive could pull at speed with a fraction of the fuel? The idea was not merely to build a new train, it was to reinvent the economics of passenger rail from the wheels up. The design that emerged from General Motors' styling studios was unlike anything American railroads had seen. The locomotive was a modified EMDLWT-12, a lightweight unit producing 1,200 horsepower from a single 12-cylinder diesel engine. Two smaller auxiliary diesel engines provided onboard electrical power, but contributed nothing to propulsion. The nose was sculpted into a dramatic aerodynamic shape that owed more to automotive design than locomotive engineering. It looked like a concept car stretched to rail proportions. But the real gamble was behind the locomotive. Instead of purpose-built railroad passenger cars, General Motors mounted modified General Motors bus bodies onto rail trucks. The logic was elegant in a corporate sense. General Motors already mass-produced bus bodies by the thousands. The tooling existed. The supply chain existed. If you could adapt those bodies for rail use, you could build passenger cars at a fraction of the cost of traditional Pullman or Bud construction. Each car seated roughly 40 passengers in aircraft-style reclining seats. The cars were short by railroad standards, around 40 feet, compared to the 85-foot cars that were standard on most American railroads. They rode on two-axle trucks with air suspension, another technology borrowed from the highway world. The interior was designed to feel modern. Large windows, bright lighting, that particular brand of mid-century optimism that promised everything would be better, faster, cleaner. 2 complete train sets were built. General Motors intended them as demonstrators, to be tested on major railroads and then sold in production quantities once orders rolled in. The entire program was built on the assumption that once railroad executives saw the economics and passengers saw the styling, the orders would follow. Pause for 1 second. General Motors launched the Aerotrain with a publicity campaign that rivaled anything the automobile division was doing. The train was displayed at auto shows. It appeared in magazine advertisements alongside Cadillacs and Corvettes. Press runs were organized on multiple railroads, with journalists invited to experience the future of rail travel at speed. The Pennsylvania Railroad tested it between New York and Pittsburgh. Union Pacific ran it on the City of Las Vegas service between Los Angeles and Las Vegas. Rock Island put it on the jet rocket between Chicago and Peoria. The early press coverage was enthusiastic. The styling was photogenic. The speed was respectable, with the demonstrators capable of reaching around 80 miles per hour in testing. General Motors filmed promotional footage of the Aerotrain streaking across the American landscape, nose cone gleaming, looking for all the world like a spacecraft that had decided to stay on the ground. For a brief window, it seemed like General Motors might actually pull it off. The railroad industry was desperate enough for a solution that even the most conservative operating departments were willing to try something radical. The problems started almost immediately, and they all came from the same source: the ride quality. Those lightweight bus bodies on two-axle trucks with air suspension behaved nothing like traditional railroad passenger cars at speed. A conventional 85-foot car on two four-axle trucks distributes its weight across 8 axles and rides with a stability that generations of railroad engineering had refined. The Aerotrain cars were short, light, and mounted on suspension designed for highway speeds of 60 miles per hour, not railroad speeds of 90 or 100. At speed, the cars developed a lateral oscillation that passengers described in terms that left no room for interpretation. They pitched, they yawed, they swayed in a rhythm that induced nausea in a significant number of riders. The lightweight construction meant that every rail joint, every switch frog, every slight imperfection in the track transmitted directly into the passenger compartment with a sharpness that heavier cars simply absorbed. Railroad men understood the problem immediately. Weight is not just a cost in railroading. It is stability. A 90-ton Pullman car does not bounce because 90 tons of steel does not bounce. The laws of physics do not care about styling or economics. You cannot cheat mass. What GM had built was essentially a highway vehicle forced to operate in a railroad environment, and those are two fundamentally different dynamic regimes. The air suspension that worked beautifully at 55 miles per hour on smooth concrete became actively punishing at rail speed on jointed track. The Pennsylvania Railroad delivered the clearest verdict. Business travelers, the only segment still choosing trains over planes for certain corridors, wrote letters of complaint. They told their colleagues. They switched to competing services or drove. The PRR had staked the Aerotrain on routes where its reputation for smooth, comfortable travel was a competitive advantage, and the Aerotrain was destroying that reputation one trip at a time. The railroad quietly pulled it from premium intercity service after making it clear that no amount of futuristic styling could compensate for a ride that left passengers reaching for the armrests. Union Pacific's experience told a different but equally damning story. On the City of Las Vegas run between Los Angeles and Las Vegas, passengers actually enjoyed the onboard amenities. Union Pacific offered a free buffet and bar service, and riders responded well. The problem was not in the seats. It was under the hood. The Aerotrain's 1,200 horsepower locomotive simply did not have the muscle to handle the grades on the route. Climbing Cajon Pass, the train set needed a GP9 helper locomotive coupled on just to make it over the summit. A train that required a second locomotive to do the job of one was not a cost savings. It was a contradiction. Union Pacific pulled the service after roughly 9 months, not because the passengers rejected it, but because the machine could not do the work. 2 different railroads, 2 different failures. The PRR proved the passengers would not tolerate the ride. Union Pacific proved the locomotive could not handle the territory. Together, they proved the Aerotrain was not a solution to anything. There is an iron law in passenger transportation. You can convince someone to try a new service once with marketing. You cannot overcome physics with a press release. What makes the Aerotrain story more than just a tale of bad engineering is what it reveals about the relationship between General Motors and the American railroad industry in the 1950s. General Motors was not a railroad company. General Motors was an automobile and bus manufacturer that happened to also build locomotives through its electromotive division. The Aerotrain was designed by automotive stylists, built with bus components, and marketed with automotive advertising techniques. The fundamental assumption behind the project was that railroad passenger service was essentially the same problem as highway transportation, just on rails. That assumption was wrong, and it was wrong in ways that a railroad engineer would have identified immediately. Rail dynamics are not road dynamics. Passenger expectations on a train are not the same as on a bus. The distances are longer, the speeds are higher, and the tolerance for discomfort is lower precisely because the train is supposed to be the premium alternative. General Motors approached the problem as a manufacturing challenge. How do you reduce the cost per seat mile? A railroad engineer would have approached it as a ride quality challenge. How do you maintain passenger comfort at speed? These are not the same question, and they lead to radically different designs. The Aerotrain answered the first question brilliantly, and the second one not at all. The contrast with what was happening elsewhere in the world is instructive. In Japan, engineers were already working on what would become the Shinkansen, the bullet train that launched in 1964. The Japanese approach was the exact opposite of General Motors' approach. Heavier cars, wider gauge, dedicated track with no joints, and suspension systems specifically engineered for high-speed rail dynamics. In France, the National Railroad was developing lightweight turbine trains, but with purpose-built bogies and suspension designed from the ground up for rail service, not adapted from highway components. Both programs succeeded because they started from the rail problem and engineered forward, rather than starting from existing highway technology and hoping it would transfer. The Aerotrain's failure was not a failure of ambition, it was a failure of translation. General Motors tried to translate bus technology into railroad technology and discovered that the translation does not work at the fundamental level of physics. A bus body is optimized for a regime of forces that simply does not exist on a railroad, and no amount of clever adaptation can bridge that gap. The lightweight revolution in passenger rail did eventually happen, but it happened through purpose-built lightweight rail vehicles, not through adapted highway equipment. After the major railroads rejected the Aerotrain for premium intercity service, the two train sets did not disappear immediately. They were downgraded. Rock Island kept one in commuter service between Chicago and Joliet for several years, where the shorter distances and lower speeds made the ride quality marginally acceptable. The other unit bounced between demonstrations and secondary assignments, but the writing was on the wall. No production orders ever materialized. The grand vision of hundreds of Aerotrains replacing conventional equipment across the American rail network died quietly in railroad operating offices, where the passenger complaint files and mechanical reports told the whole story. By the mid-1960s, both train sets were retired. The program that was supposed to save American passenger rail had instead become a cautionary tale about what happens when you let the marketing department drive the engineering. The cost savings that looked so compelling on General Motors' spreadsheets meant nothing if the train could not climb the grades and the passengers would not come back. And on the Pennsylvania Railroad, the passengers would not come back. One Aerotrain survives today at the National Museum of Transportation in Kirkwood, Missouri, near St. Louis. The other is at the National Railroad Museum in Green Bay, Wisconsin. They sit there looking exactly as futuristic as they did in 1956, all swept lines and jet age promise. Visitors photograph them and marvel at the styling. Nobody asks to ride in one. Perhaps that is the most honest legacy the Aerotrain could have, a machine that looks like the future but feels like a mistake. The space age came to American railroads, and American railroads sent it back.